Hello, in this video lecture we are going to discuss the diagonalization and decomposition, that is how given any square matrix, 2 by 2 matrix, 3 by 3 matrix, how we can convert that matrix into a diagonalized matrix, and then how we given any square matrix, how we can decompose that particular matrix, particular square matrix into different components, into different matrices. The first concept that we are going to discuss is the rank of the matrix. The rank of the matrix is defined as the maximum number of linearly independent rows or column vectors in the matrix, or the maximum number of linearly independent rows vectors in the matrix. Both definitions are equal or equivalent. So we are looking for maximum number of linearly independent column vectors or maximum number of linearly independent row vectors in the matrix. That is known as the rank of the matrix, or in simple words, we can say that the rank of the matrix is how many rows are unique, how many rows or column vectors in the matrix are unique. They are not made up of the other rows or vectors. Now for any matrix, let's suppose for an R cross R by C matrix, if R is less than C, then the maximum rank of the matrix is R. If R is greater than C, then the maximum rank of the matrix is C. In simple words, if we are given any matrix A whose dimension is R cross C, it has R rows and C columns, so then its rank, of A will be less than or equals to minimum of R comma C. If rows are less, then the maximum rank of matrix A will be equals to R. If C is less, then the maximum rank of the matrix will be C. Now let's discuss some examples regarding this. So let's suppose we have this matrix A, 1 2 3, and then 3 6 9. Now the dimension of this matrix is 2 cross 3. It has 2 rows and 3 columns. So the maximum rank of this matrix will be 2. And now we have defined the rank of the matrix as how many rows are unique, how many columns or rows are unique in the matrix. So so from here we can see that second row is equals to first row multiplied by 3. If you will multiply the first row by 3, we will get the second row. Second row is 3 times the first row. So the rank of this matrix is particular matrix is 1. So the rank of this matrix is not 2. So let's suppose we had this case, we have this almost the same matrix, 1 2 3 and then 6 and 9. Now the rank of this matrix will be 2, because we cannot compute the second row by the first row, like here. So the rank of this matrix in this first matrix is not 2, it is equals to 1, and the rank of this matrix is, this particular matrix is 2. Now let's discuss the other example. We have 1 2 3 0 2 2, and then we have 1 4 5. We have this matrix, let's suppose matrix B. Now this matrix B have 3 rows and 3 columns, so the maximum rank of this matrix will be 3. Now we have to see how many rows or columns in this matrix are unique. Now if you see closely, you will see that the third row is equals to first row plus the second row. Like 1 plus 0 is 1, 2 plus 2 is 4, and 3 plus 2 is equals to 5. So as a result, rank of this matrix B is equals to 2 rather than 3. So basically in the rank we are just going to look at how many rows or column vectors are unique, they are not made up of the other. So let's have the last example. 1 2 3, and then we have 0 2 2, and then 0 minus 2 and minus 1. So in this matrix, let's call this matrix C. So it has 3 rows and 3 columns, so the maximum rank of matrix C is 3, because minimum of 3 and 3. Now this could be the maximum rank of this matrix C, but now we have to see is any row or column made up of the other rows or not. So now if you look closely, we can see that the third row here is equals to first row minus 2 times the second row. 1 minus 2 times 0 is 0, 2 minus 4 is minus 2, 3 minus 3 minus 4 is minus 1. So we can compute the third row by using these two rows. So this implies that rank of matrix C is not C. Rank of this matrix C is equals to 2. So now the next thing is how we can compute, given any matrix, how we can compute its rank. So rank is equal to the dimension of the largest square submatrix of A that has a non-zero determinant. So let's suppose we are given this 4 by 4 matrix. So now if you compute the determinant of this 4 by 4 matrix, this is let's call this is my A matrix. So now the dimension of matrix A is 4 by 4. So the maximum rank of this matrix, the rank of matrix A, the maximum rank of matrix A would be equals to minimum of 4 comma 4, which is equals to 4. So the maximum rank of matrix A could be 4. So now if you compute the determinant of this 4 by 4 matrix, you will see that determinant of this matrix A or this 4 by 4 matrix is equals to 0. So determinant of this matrix A is 0. So this implies that rank of the matrix A is not 4. So now we have checked the determinant of this full matrix. Now we have to check the determinant of next sub matrix, this matrix. Now if you see the determinant of this matrix, 4, 5, 2, 3, 9, 6, 8, 10, 7, this is equals to 633, which is not equals to 0. So this implies that rank of this matrix is 3. So again, rank of the matrix is equals to the dimension of the largest square submatrix. It is equals to the largest square submatrix of A. Suppose this determinant, this 3 by 3 determinant is also 0. So then what we will have to do, we will go and check the determinant of this submatrix, and if that determinant is not 0, is non-zero, so then the rank of that matrix will be equals to 2, and so on. So in the previous example, you can see that as we have defined the rank of the matrix as the maximum number of linearly independent rows or column vectors of a given matrix, of matrix A. So now you can see that first column plus twice the second column plus 0 times the third column minus 1 multiplied by the fourth column is equals to 0. So this implies that rank of the matrix is not 4. So this is, and the next thing is, if A is a square matrix, if A is n by n, the rank of matrix A is n if and only if A is non-singular, or if A is n by n, then rank of matrix A is n if and only if determinant of A is not equals to 0, then that matrix A will have a full rank. If A is a non-singular matrix, means determinant of matrix A is not equals to 0, then rank of the matrix will be equals to n. The first statement and the second statement, they are same. If the determinant of matrix A is not equals to 0, then that matrix A will have a full rank. and if A is n by n matrix and rank of matrix A will be less than n if and only if A is a singular matrix. It means that determinant of that matrix A is equals to 0. If the determinant of any given matrix A is 0, then rank of that matrix will not be full. It will be less than the number, it will be less than minimum of rows or columns. If determinant of matrix A is equals to 0. Now let's try to look at these examples in Python and do some practice there. So first of all, we have to import the libraries, import NumPy as NumPy, and the second library is regarding the plots. If you want to graph or plot anything, so write down these two, import space NumPy as NP and press shift plus enter. Now the next thing is we are going to define a matrix. Let me do the first example which we have done. We have defined a matrix with the name of M. Now the next command to compute, we have just defined the matrix M. Now to compute the rank of the matrix, the command is numpy dot linear algebra LINALG dot matrix underscore rank, and then within brackets we'll write down the name of the matrix, and now press shift plus enter. So now the rank of this matrix is equals to 1, as we have seen previously. Now nextly, I'm going to generate the next example, 1 2 3, and then the second row was equals to 0 2 2, and then next row 1 comma 4 comma 5, and now press shift plus enter. So I have just defined the matrix M. Now if I want to find out the rank of this matrix, so R A underscore M equals to numpy dot linear algebra dot matrix underscore rank, and press shift plus enter. So now the rank of this matrix is equals to 2, because the third row is equals to the first row plus the second row, and so on. So now let's try to compute the rank of the matrix, that 4 by 4 matrix. So now first of all I have to define that matrix. I'll write down the first row, So my first row is equals to 4 comma 5 comma 2 comma 14, and then I will write down the second row within these square brackets, 3 comma 9 comma 6 comma 21 comma third row within the square brackets, 8 comma 10 comma 7 comma 28 comma the last row within the square bracket, 1 comma 2 comma 9 comma 5. So I can press shift plus enter. So where is the error? So error is here, I need to have a comma rather than point, and now press shift plus enter. So that was the error. So now we have defined the matrix A. Now if I want to find out the rank of this matrix A, so I can write down this command. I can write down r underscore A equals to numpy dot linear algebra dot matrix underscore rank, and then within bracket I am going to write down matrix A. Now the next thing is I can go ahead and write down print r underscore A and shift plus enter. So now the rank of this matrix, that matrix, is equals to 3. So now we have computed the rank of this matrix, which is equals to 3. So we have a 4 by 4 matrix which has 4 rows and 4 columns. So it means that determinant of this matrix A is equals to 0. It is equals to 0, which we can confirm from here. If the determinant of any given square matrix is non-zero, then the rank of that matrix will be equals to n. So determinant underscore A numpy dot linear algebra dot det for determinant, and then within bracket I can write down the name of that matrix and just print det underscore A, so you get 0. So the determinant of of matrix A is 0. So this implies that rank of this matrix is not equals to n, which means rank of this matrix is not equals to 4. And now what we can, according to this definition, what we can go ahead and do is check the determinant of next submatrix, largest square submatrix. First of all, we have checked the determinant of 4 by 4 matrix. If it is 0, then what we'll go ahead check the determinant of next largest submatrix, that is 3 by 3, like this. If determinant of matrix A is, let's suppose, non-zero, so then finish, rank of the matrix will be equals to 4. If the determinant of the matrix, if this matrix is 0, then it means that rank of that matrix is not 4. Rank of the matrix is less than 4. Now the next step would be, we'll go ahead and check the determinant of largest submatrix, this 3 by 3 matrix. If the determinant of that largest submatrix is non-zero, then the rank of that matrix will be 3, and so on. So nextly we will check the determinant of that matrix. So I guess I have already defined the determinant. let me call this as A1. So this is the 3 by 3 matrix. So det underscore A1 equals to numpy dot linear algebra dot det, and then bracket start A1 and shift plus enter. So just we have to first check the determinant of this A1. So the determinant of this matrix A is 63 or 62.99, so which implies that determinant of this original matrix A is 3. Nextly, what we can do is we can do some practice regarding the random matrices. So first of all, what we can do is we can define a random matrix. So M is equals to 4 and N is equals to 4. Number of rows and number of columns are equals to 4. And then we are defining a random matrix by using this command A equals to numpy dot random dot randn, and then the first element is M comma N, and M is equals to 4 and N is equals to 4. Now just print A. Now each time you will run this command, you will see that the elements of this matrix A will change. So that's why this is called as the random matrix. So because these are the random elements, so it implies that none of the columns will be made up of the other columns, or none of the rows will be made up of the other rows. So the rank of this matrix, of this particular matrix, is expected to be 4, because all these are the random elements. Because all these, in this case, all the elements, all the column vectors are unique. They are not made up of the other column vectors. Similarly, all the row vectors are unique. They are not made up of the other row vectors. So that's why we are getting the rank of this matrix 4. This is the 4 by 4 matrix, and its rank is equals to 4. And if you check the determinant of this matrix, det underscore A equals to numpy dot linear algebra dot det, and then within bracket write down the name of the matrix and press shift plus enter. So here there is one error, lin algebra, shift plus enter, and now print det underscore A and shift plus enter. So the determinant of this 4 by 4 matrix is not equals to 0. So this will imply that the rank of this matrix is full, or the rank of this matrix is equals to 4. So now let's try to do one thing. We are defining another matrix, that is B equals to A. We are defining another matrix B, and B is equals to matrix A. So this is my matrix 4 by 4 matrix A, and this is my B matrix 4 by 4. Now what we are going to do is we are going to set the first column equals to the fourth column. Shift plus enter, by using this command b square bracket start colon comma and -1 equals to b square bracket start colon comma and -4. Now let's try to see the B matrix. Now you can see that the first column and the last column, they are exactly same. So we have set the first column or we have set the fourth column. We have set the fourth column equals to the first column. Now just guess what should be the rank of this matrix, because the first column is exactly equals to the fourth column, or fourth column is exactly equals to the first column. So the rank of this matrix B, this matrix B will not be 4. It will not be, its rank will not be full. Now we can verify using this command. So the rank of this matrix is not 4, it is less than 4, which is 3. And if you check the determinant of this matrix B, it is expected to be 0. And this is 0 because this is in scientific notation. This here we have E, so it implies that this term is 0 and the non-zero element starts after approximately 16 digits. So the next thing that we are going to see, look at is that determinant of rank of A and A transpose, they are same. So we can define any matrix M just compute the rank of this matrix. So the rank of this matrix is 3. This rank is full. Now what we can do is, next we can go ahead and we can first of all compute the transpose of this matrix. We can take the transpose of this 3 by 3 matrix, and then we are going to compute the rank of that transpose matrix. Now you will check that the rank of that transpose matrix is also equals to 3. So you can go ahead and practice. Some further examples, and you will see that the rank of the matrix, rank of the original matrix and the rank of the transpose matrix, they are same. They are exactly same. And that's all for this video regarding the rank.